Satyabama Institute of Science and Technology, Chennai. Satyabama Institute of Science and
Start.
Sure, I'll start. Yeah. Okay. Very warm good afternoon to all of us gathered here. So, on behalf of the Department of Physics, I welcome you all to this 2 weeks FDP on pursuit of excellence in research and advanced technology. We will begin the session with a prayer song sung by Master Vasudayan. Vasudayan, can I have you for the prayer song?
சீராரும் வதனம் என திகழ்வரத கண்டமிது தெக்கணமும் அதில் சிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை நுதலும் தரித்தனமும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே உன் சீழமை திறம்பியர்ந்து செயல் மறந்து வாழ்த்துதுமே
Yes, thank you, Vasudayan, for that song. As we know, Satyabama is a prestigious institution which excels in the field of engineering, science, and technology for more than 3 successful decades. And the college offers multidisciplinary academic programs in various fields of engineering, science, technology, law, dental science, pharmacy, nursing, management, arts and science, and allied health sciences. And the institution has been ranked in 40th position by NIRF Government of India among the universities in India for the year 2021 and ranked 1 among the top 50 universities for 5 consecutive years. Our founder chancellor, Colonel Dr. JPR, established Satyabama Engineering College in the year 1988 with the aim to provide opportunity to deserving students to pursue engineering education. He has dedicated the later part of his life to the cause of education, and we are ever indebted to our founder chancellor, sir. And we also thank our Chancellor Madam, Dr. Maria Zina Johnson, our President Sir, Dr. Marie Johnson, and Dr. T. Sasiprabha Madam, our Vice Chancellor, and our entire management team for providing us opportunities to conduct such academic programs. And this objective of this FDP for a topic on pursuit of excellence in research and advanced technology is specially to benefit our PG students, researchers, and faculties of physics, chemistry, mechanical engineering, and nanotechnology to enlighten latest research development of materials and their technological applications. The main objective is to explore career developments in materials and to address new challenges and solutions, and also to motivate them by interacting future research direction. It also discusses how the various methods can drive to the understanding, improvement, and predictions of new technology-based engineering materials and its applications. So now I welcome Dr. T. Sasiprabha Madam, Vice Chancellor, Satyabama Institute of Science and Technology, to inaugurate this FTP. And Madam has completed her graduation in Computer Science and Technology and has started a career as lecturer in the Department of CSE in our college in the year 1995. From then, Ma'am has grown professionally in a span of 25 years, proving her teaching abilities and operating several research projects worth 125 lakhs as principal investigator. All through her career, she has been distinguished by her unique working style and has been a key person who has contributed to the development of various new initiatives of the institution. She has more than 100 publications to her credit, and to us, always an ever inspiring role model. And it is a great honor to have you, Madam, here. We welcome you, ma'am, and request you to inaugurate the FTP for us. Ma'am?
Yeah, thank you.
Yes, ma'am.
So good afternoon to all the participants, speakers, and the organizers. I think Department of Physics is vigorously organizing more FDPs, conferences. It is very good to see that every faculty member in the Department of Physics is capable of organizing and identifying good speakers for the benefit of this academic community. So this 2 weeks FDP on pursuit of excellence in research and advanced technology, organized by Department of Physics, is, I think it's really important, because Department of Physics is playing a huge role in any technical education or any institution which is having technical programs, not only on research. So towards technology developments, the concepts of physics are very, very important. And the faculty here have identified good speakers. I think the participants have understand the various sessions in this 2 weeks FDP. I hope all these sessions will be of enriching to you, because they identified the right speakers in every session. So really, I'm appreciating the Department of Physics and the organizers specifically. So for having organized this wonderful FDP, and you keep organizing this program for the benefit of this academic fraternity. And I could able to see the speakers from other countries also. So I really appreciating all the participants who are here, because they have organized this program more convenient for the participants to attend. I think all the sessions are scheduled in the afternoon session, and I hope it is convenient for the working professionals also to attend this program and get benefit out of this. Once again, I am appreciating the Department of Physics and the HOD and the organizers, organizing secretary, the conveners for organizing this 2 weeks FDP program. So organizing a 2 weeks FDP program is not that much easy, because organizing a single day or 2 days is okay. 15 days continuously they need to concentrate on, they have to make the participants attentive on all those sessions. They have to keep communicating with the speakers, and they have to alert the speakers before, after. So a lot of coordination is required. I hope the department will do it efficiently. And once again, I am congratulating and appreciating all the participants for this 2 weeks FDP. So thank you, ma'am. Thank you. So all the best.
Thank you, ma'am. Yeah.
Thank you so much.
Thank you, ma'am, for that encouraging and motivating words. And I think without your support, this FDP is not going to be possible for us. And I also thank all the participants for joining this inaugural session. Thank you, ma'am, especially amidst your busy schedule. Thank you, ma'am, once again.
A very good afternoon to one and all present here, and thank you for joining with us. Before I introduce our speaker, Dr. Farooq Balipina, I should thank our speaker for his great consideration. So thank you, sir. Thank you so much, because we are 9 hours 30 minutes. We are ahead of them, even though SAR has accepted immediately, and he considered only participants convenient and the conveners convenient. So thank you so much for your great support, sir. So we cordially invite our speaker, Dr. Farooq Balipina, Binghamton University, State University of New York for the first session of FDP on Pursuit of Excellence in Research and Advanced Technology from 20th October to 30th October 21st. Farooq Balikna sir received his BS degree in Electrical Engineering from Yildiz Technical University and MS degree from Istanbul Technical University, Turkey. He had PhD degree in Electrical Engineering from Binghamton University, State University of New York in the year 2018. He worked in the field of thin film solar cell microfabrication at the Center for Autonomous Solar Power during his PhD. In the year 2016, he held a visiting researcher position and worked on flexible solar cell research project in Oregon National Lab. He continued his postdoctoral research at the Center for Advanced Microelectronics Manufacturing in the Binghamton University. During his postdoc, he worked on the microfabrication of transparent semiconductor and RF antenna and flexible substrate. His research focuses on 2D semiconductors for optoelectronic applications and the microfabrication of RF integrated circuits. In this talk, Sir is going to present the synthesis and characterization of the metal sulfide and organic perovskite semiconductors for their applications in thin film solar cells. The microfabrication and characterization results of tin sulfide semiconductor will be mentioned. The higher transmittance of N-type cadmium oxysulfide was used as an alternative in order to increase the visible range of transparency, and this film can enhance the visible light reaching to photoabsorber that helps in the increment of photovoltaic efficiency. The photovoltaic applications of these materials will be explained. So I hand over the session to Sir.
Okay. Thank you, Dr. Angela.
Thank you, sir.
First of all, thanks for having me. I'm honored to be part of this wonderful organization FDP program. So let me share my screen first. Okay. Hello, everyone again. Today, I'll be talking about emerging thin film semiconductor materials for solar cell application. Firstly, I'll give brief information about new photoabsorber material, and then share my experimental results from my PhD dissertation. First of all, let's look at the Binghamton University research facilities first. The S3IP is small-scale system integration and packaging center. It's kind of like an umbrella research division. Under S3IP, there are several research centers. First one is Northeast Center for Chemical Energy Storage Division. Maybe you guys are familiar. Dr. Stan Whittingham won Nobel Prize in Chemistry in 2019. He is the director of this research group. They mainly focus on lithium-ion batteries and supercapacitors. Another research center is ES2, Energy Smart Electronic System. They have focusing on electronic packaging, designing, and data cooling research topics. IECC and ADL are the facilities for material characterization. These labs are open for both academia and industry. CASP is Thin Film Research Group. CAM is Center for Advanced Microelectronic Manufacturing. So I had PhD under Professor Alok Rastogi. He's my advisor. So I mainly focused on thin film solar cells based on the metal sulfide, tin sulfide, and cadmium oxysulfide, and organic perovskite semiconductor. There were two main topics in my PhD. The first one, develop thin sulfide P-type semiconductor. Second one is modified the common cadmium sulfide, the conventional one. So we modified the cadmium sulfide N-type semiconductor and called it like oxysulfide. And the last one is perovskite. As a postdoctoral researcher, I continued to work at CAM under the advisor of Professor Mark Pollex. Roll-to-roll is very unique facility. I had an opportunity to work in this facility. So it's kind of like microfabrication process for flexible electronic device. So we developed IZO, indium zinc oxide transparent semiconductor for optoelectronic application, and worked on flexible RF antenna devices. The flexible glass, maybe you heard the name, the company name, Corning, is a very strong partner of Binghamton University. So they has the flexible glass substrate. Instead of using the PET, PEN, or polyamide plastic substrate, flexible glass substrate becoming more attractive for flexible electronic device. First of all, so we'll look at this graph. This is very common, everyone working in the PV research. NREL PV chart. It's called NREL PV chart. NREL is National Renewable Energy Lab. Was supported by DOE, United States Government Department of Energy. NREL has facilities for almost all renewable energy research. Solar research group is also kind of like really large, and they almost mainly focusing on all research solar cell types. This chart basically shows the highest efficiency of each solar cell and which institute or research group or like companies holding this highest efficiency based on the year. So it also gives an idea about types of solar cell. So mainly in the literature, solar cells are categorized into three major parts. The first one is the first generation is the crystal silicon solar cell, the blue one. Green one is thin film technologies. Brown one is emerging PVs. The purple one shows gallium arsenide solar cell and the multi-junction solar cell. So thin film categories after silicon solar cell, the cadmium telluride was the first one. It was already commercialized, kind of more stable. After cadmium telluride, the CIGS was the second commercialized one. After CIGS, the emerging PV solar materials started like after CIGS technologies. The cadmium telluride has cadmium material. It's kind of toxic. So the people started to search different material. CIGS was the first candidate. After that, so they moved to CZTS. Like the copper, tin still there, but they focused to zinc and tin as well. So emerging photoabsorber material, we can basically categorize into three major parts. The copper chalcogenide related to CIGS. The CZTS, as I said, is the most attractive one after CIGS. After that, the copper tin sulfide, copper tin selenide, antimony selenide, antimony sulfide, these are the other candidates, common candidates. The second category is binary chalcogenide related to cadmium telluride, tin sulfide, antimony selenide, antimony sulfide. And in last category, everybody knows that the perovskite is the last emerging photoabsorber material. So this graph basically shows the number of publication and the world record efficiencies for the emerging photoabsorber material. So emerging photoabsorber materials have been published like since 2008, seems most attractive for all researchers in this field, but there are many things need to be done in this field because the emerging photovoltaic efficiencies are still around 5%. So in terms of the material science and engineering, electrical engineering, so there are many things needs to be developed and discovered in this field. Okay, let's start. First part, I'll give information about the thin film, thin sulfide, thin film semiconductor processing and material characterization for solar cell application. Okay, so thin sulfide, thin sulfide has three main phases: thin sulfide, SNS2, SN2S3. So in terms of the low ionization energy and higher hole concentration, so we're looking for perfect p-type thin sulfide in order to use in solar cell. So SNS2 is N-type, SNS and SN2S3 are p-type semiconductor. In terms of the deposition, thin sulfides have been deposited by various methods: vacuum evaporation, atomic layer deposition, sputtering, chemical bath deposition, chemical spray pyrolysis. There are various methods in the literature. So in my experiment, so we mainly focused on the investigation of thin sulfide deposition by sulfurization from TBDS source. First, RF sputter metallic layer sulfurized used TBDS source. Okay, so this is the experimental setup. So we put the substrate in the middle of the furnace, and the TBDS source was placed in this glass bubbler and heated, kept the 100° below the boiling point of this liquid. So once the furnace reached the desired temperature, by opening the valve, the sulfur comes through this valve and the sulfurization starts. TBDS sulfurization for thin sulfide material was the first application for its kind in the literature. We developed it. So there are the TBDS has some kind of advantages over the other sulfur source. H2S, elemental sulfur source, other candidates as a sulfur source in the literature. TBDS is low toxic, low cost, and doesn't require extra handling during the sulfurization process. So it was wonderful experience for me to develop the thin sulfide film through the TBDS source for the first time in the literature. So in this research, 100 nanometer RF sputter metallic film sulfurized for fixed time, 90 minutes, for various temperature, 300, 350, and 400 degrees. The sulfurization thin sulfide film growth has two steps. Basically, in the first step, the sulfur atoms bonding with tin atoms, firstly on the surface of the film, then diffuse across the thickness of the metallic layer. In the reaction one, tin started to sulfurize with sulfur vapor and becoming thin sulfide. So the critical step is we want the pure, highly crystal and highly dominant tin sulfide. So time optimization is really important between reaction 1 and reaction 2. Moving to material characterization is critical step after processing thin film. So we have 3 films, 300, 350 and 400. So the XRD characterization was the first one to identify the phase of the material. So once look at the 300, so there are 3 dominant tin sulfide phase, and the blue one shows 350 degree. It has several planes, several phases from other phases as well. But in terms of the number of peaks, it has dominantly tin sulfide phase. 400 degree is definitely, we can definitely see there is like a significant reduction in the intensity of these diffraction lines, and mainly belong to other phases, like called secondary phases, SN2, S3. So in terms of the number of peaks, basically 350 degree shows a higher number of peaks belongs to tin sulfide. So according to XRD results, so tin sulfide is already start to initial phase at 300 degree, but highly crystal, more dominant tin sulfide became at 350 degree. Raman spectroscopy is like kind of light scattering technique, basically gives an idea about phase identification as well. So according to theoretical papers from the literatures, tin sulfide has various active modes and 7 infrared active modes. So these theoretical results shows, it was published 1975. It is like almost main reference for the Raman analysis of tin sulfide material, and that analysis shows the peak around 300 match wells with secondary phases. So basically, once look at our Raman spectra analysis, the peak started to occur around 300 Raman shift in 400 sample, 400 degree sample. So basically, Raman and XRD reports match very well. The 350 promotes to highly crystal and dominant tin sulfide, but higher temperature, 400 degree, shows secondary phases, kind of like mixed phases, both SNS, SNS2, SN2, S3. Yeah, optical analysis is the important step for the application of solar cell. So basically, once we look at the 3 samples of the optical transmission, all of them show very sharp absorption thresholds. So basically, these are good candidates for solar cell application. So according to Umbert's law, based on the absorption coefficient and thin film thickness, and using the transmission data, using the extrapolation of in the specific region of tau relation, we can basically calculate the direct and indirect band gap of the material. So for 3 sample, calculating the tau relation for direct and indirect band gap, we calculated. But the DFT studies in the literature shows tin sulfide has 1.1 indirect band gap, SNS2 2.24 indirect, SN2S3 1 to 2 indirect band gap. And experimental research shows in the literature both indirect and direct band gap. From our transmission data, we calculated both indirect and direct band gap. So 350 sulfurized film, basically very close to theoretical and experimental values, 1.1 EV for indirect, 1.56 EV direct. Okay, so for the first time, using the TBDS low cost, low toxic sulfur source, we developed the tin sulfide thin film photoabsorber material. So in the atmospheric pressure. So second part is the N-type in the solar cell device. Cadmium sulfide is very common for cadmium telluride, CIGS, CZTS, for many type of inorganic thin film materials for the solar cell. So because it has very perfect band alignment with the P-type in terms of these advantages. So basically, many people prefer to use cadmium sulfide. So CBD is the common technique for the CDS. Even the some industries in CIGS and cadmium telluride, they use the chemical bath deposition technique for commercialized solar panel technologies. So we use the same technique. The only modification and challenging part in this research, in this project, is adding TX100 surfactant. So we created an alternative chemical bath deposition to form oxysulfide material, cadmium oxysulfide. Basically, we modified the common technique, the conventional technique, by adding TX100 surfactant. So what was the main improvement? And I'll share the result in the following slides. So there was an increment in the visible range of transparency without any decrease in the thickness of CDS growth. We have definitely same thickness, CDS and CDSO, but there was an incredible increase in the visible range. So there were 3 setups in terms of the deposition time. Basically, it only changed the thickness of the film, 10 minutes, 15 minutes, and 20 minutes. So, and also other thing is, so use 4 sample with the various concentration of TX100. The bath C is the conventional one, which forms only CDS, and other bath provides various CDSO films. First analysis for the CDSO is CDS and CDSO is Raman. So basically, we have 4 setup based on 3 different deposition time, 4.5 volume concentration, and without TX. So according to the Raman charts, the curve B is the cadmium oxysulfide, and this peaks around 1,000 Raman shift is originating from cadmium oxide. So basically, the film shows both phases, cadmium sulfide and cadmium oxide. Looking at the XRD results, there is no radical change in 2 theta position for these samples, but once analyzing with Gaussian peak fitting, we can get some extra peak which are originated from cadmium oxide phase. So basically, XRD and Raman results match. So we have cadmium oxide and cadmium sulfide in the phase. So this is the critical part, the optical analysis. For films, the black one is the common CDS, and the top one is the purple one is the CDSO film with the concentration of 4.5% TX standard surfactant. So basically, the optical transmission range, there is a significant increment. In the common CDS, in this region, it is 70%. In the cadmium oxysulfide, it reached to 90%. So basically, through this improvement, we expected cadmium oxysulfide films, higher transmission films, less absorption over the visible spectrum. So basically, through this advantage, higher number of visible photons reach the p-type, and this might help the efficiency increment. Again, tau relation is the common technique for band gap calculation from the transmission data. So literature, DFT, and some experimental results shows the cadmium sulfide band gap is 2.42 EV and cadmium oxide is 2.16 EV. So based on the results we calculated from the transmission data, we have our cadmium oxysulfide is between these two, the band gap value of cadmium oxysulfide material. The XPS shows a very clear result compared to XRD and Raman. So based on the concentration, looking at the black color, no TX standard surfactant additive, which forms only CDS, and the green one is the highest concentration of TX standard surfactant, which provides the higher oxygen concentration in the film. The oxygen concentration increased with the increment of TX standard surfactant. So basically, the oxygen concentration increased with the increment of TX standard in the formation of CDS. As a conclusion from this work, we investigated the conventional CDS1. We modify it by the additive of TX standard surfactant, which results the cadmium oxysulfide in an alloy of cadmium sulfide and cadmium oxide in the visible range. And part 3. So this is the combination of part 1 and part 2 as an application of solar cell, tin sulfide based solar cell. So as I mentioned in the beginning of the lecture, so this is tin sulfide is the emerging photoabsorber material candidate for the solar cell application. The efficiency is not that high, still around 5%. The highest efficiency is still around 5%. So this chart basically shows the open circuit voltage, short circuit, open circuit and short circuit, open circuit voltage and short circuit current, fill factor, efficiency, and based on the year. So the highest one is the latest one, MOSNS2, SNS, zinc oxide, and ITO-based structure. The highest number of the efficiency was succeeded by MIT. Was very famous in this field, and they succeed 4.4 efficiency. So in the literature, basically there are two types of the structure for solar cell application. First one, basically solar cell deposits over the moly-coated substrate. This called the substrate structure. And in the figure A, the sunlight comes through the contact. Moly substrate is on the bottom side. In the superstrate structure, this thin solar cell are deposited over the transparent conductive oxide, and sunlight comes from this side. Basically, we can say the superstrate or the substrate structure have some advantages over the other one. We can't basically say so this has better, this has more advantages, but the superstrate structure is kind of simple compared to substrate structure. Basically, it has two contacts and p-type and n-type. So that's why we wanna try our solar cell fabrication on the superstrate structure. Our solar cell structure is ITO, indium tin oxide substrate, zinc oxide, cadmium sulfide, and cadmium oxysulfide as an n-type, tin sulfide as a p-type, and silver top contact. So from the first part, we developed thin photoabsorber layer, thin layer, 100 nanometers. But this thickness is not enough to absorb photons and convert to electricity. So basically, we need thicker tin sulfide development. So based on the results we had from first part, 350 degree in our experimental setup was the optimum temperature to develop initially and dominantly tin sulfide phase, but we need thicker layer. So instead of sputter 100 nanometer layer, we used 500 metallic tin layer, again at 350 sulfurization time for various time in this one. So Raman in the bottom side, only metallic tin layer was analyzed through Raman spectra. After that, 150, 180, 210, and 240 minutes based on the sulfurization time. So basically, these charts have an idea which temperature provides the dominant tin sulfide, and after what time provides highly dominant tin sulfide, and after what time the secondary phases already started to form the entire field. So based on the Raman analysis, so 210 minutes is the optimum sulfurization time to form 500 nanometer RF sputter metallic tin layer at 350 degree to form a highly dominantly tin sulfide field. So again, the XRD spectra shows again there are secondary phases, but dominantly tin sulfide phase is available on the field. After this one, moving to solar cell fabrication. So as I said, we use the superstrate solar cell device structure. The ITO coated glass substrate cutting and cleaning process, and moving to second step, the buffer and window layer deposition. So first, as an intrinsic layer, RF sputter zinc oxide, and moving to N-type layer. So there are two films, cadmium sulfide and cadmium oxysulfide. And third step is process the P-type photoabsorber semiconductor layer. Again, firstly, RF sputter metallic layer and sulfurize through the TBDS source. After that, silver evaporation contact on the top of the device. So this is the device structure. As an anti, we form like two separate cells. First one is the cadmium sulfide, and the second one is the cadmium oxysulfide. The solar cell photovoltaic measurement. So this is very critical. So maybe many research groups, labs, universities has the solar simulator, but so the main important part is to optimize the sunlight in the solar simulator. We have to use the international silicon reference solar cell, which was certified by NDEL. So we had the cell and we optimized the experimental setup and measure the dark characteristic and the light characteristic for the solar cell. So the cell one, basically tin sulfide with cadmium sulfide, and cell two, tin sulfide with cadmium oxysulfide. The cell one has 0.55 efficiency, cell two has 1.12% efficiency. So there are two parts. Basically, the efficiency is still low than the highest record. We had the motivation, but so we kind of developed the new technique. So there were many challenging points needs to be questioned to reach the higher number of efficiency in the emerging photoabsorber material. So, but we prove this point. That point is, so there is definitely increment in the cell two, which has the cadmium oxysulfide as an N-type layer. So cadmium oxysulfide helps to improve the efficiency and all solar cell photovoltaic parameters: short circuit, open circuit voltage, and fill factor as well. So Schottky-Kastler limit basically has an idea for all type of semiconductor, what is the acceptable and the highest efficiency range for each material. According to Schottky-Kastler limit, tin sulfide has around 32, 33 efficiency. So this theoretically, this efficiency is the highest efficiency value for this material in the solar cell device. So, but why the efficiencies number are still low? First of all, for this kind of new material, it's like really long way and really long list needs to be done in this way for the researcher. Seems very motivating and challenging research area. But there are some problems still haven't overcome yet. Tin sulfide secondary phases formation. So we are getting dominant the tin sulfide phase, but secondary phases are still available. And tin sulfide and the other secondary phase is SNS2, and SNS2 is N-type. We want basically pure P-type. So this is very big problem for sulfur-based problem, the sulfur-based material. Another problem is tin sulfide buffer layer interface between the cadmium sulfide, cadmium oxide, or other type of N-type materials. The band offset and interface analysis must be improved. So the researchers need to focus on minimize the recombination between these two layers. And short minority carrier lifetime and diffusion length is still a problem for the thin sulfide material by itself. And device configuration is also another problem. Even we prefer to focus like basic structure, P-type, N-type, between two metallic contact. Maybe there are extra layers needs to be developed, and all layer needs to be analyzed and developed separately. So wanna mention briefly on perovskite solar cell. So we use the cadmium oxysulfide and cadmium sulfide as an electron transport layer for perovskite solar cell as well. I don't want to go through like perovskite solar cell topic because it will be, I guess, there will be another talk in different day on perovskite solar cell. But want to share just briefly about our perovskite solar cell structure. So in my perovskite solar cell, so we use this structure, perovskite, spiral method, and between FTO and silver band contact. Our electron transport layer is cadmium sulfide or cadmium oxysulfide. So from this research, the optimization of electron transport layer and implementation of cadmium sulfide and cadmium oxide for perovskite solar cell as well. Three sets of different electron transport layer for perovskite: 40 nanometer, 55 nanometer, and 80 nanometer for cadmium sulfide based perovskite and cadmium oxysulfide based perovskite. Again, band gap calculation from these two sets. Yeah, so this chart basically for all thickness, the black ones are the cadmium sulfide based perovskite material, and the red ones are cadmium oxysulfide based perovskite material. In all thickness, basically there is an increment. There is an increment in the cadmium oxysulfide base compared to cadmium sulfide based perovskites. But we're looking for actually the optimum thickness as well. So the optimum thickness, basically the 40 nanometer thick cadmium sulfide and cadmium oxysulfide show higher efficiencies in this one. Basically we can see from the graph is higher efficiencies compared to other one. There were two main goals: optimize the electron transport layer thickness and to get an idea about cadmium sulfide base and cadmium oxysulfide base perovskite solar cell. All right, that's all I have. Any question?
Thank you, sir. Thank you so much for giving us a wonderful and excellent talk, sir. Thank you so much. Dear participants, this is your time. This question and answer session. You can raise your questions. If you have any questions regarding this talk, you can go for it now.
Yes, sir. Two questions are posted in.
Yes, I have seen that, ma'am. It has been taken. I'll share it. Meantime, the sir can answer for this one. Sir, I'll share it now.
Yeah.
How far oxides rule over sulfide nanoparticles in the absorbing
layer? Oxide-based material, you are saying, I guess, right?
Yes.
So the sulfide-based semiconductor layers seems like more stable than the oxide-based photoabsorber materials. The oxide-based semiconductor materials are still available in the literature, but it's less than 1% efficiency. So there are many questions and problems in the oxide-based photoabsorber material in terms of the process and material development as well. I guess another question is there
any possibility of the formation of disulfide?
S2, you mean? I guess S2. So basically the sulfurization is like a, so we use like a liquid source, like as a sulfur, and developed the tin sulfide form. So basically with the formation of tin sulfide, so and with the increment of time, disulfide forms as well on the form, as we call like tin sulfide SNS2. So basically disulfide formation is possible on the film, entire the film.
Sir, one more question is there. Can I go for it, sir? One more question from, is it audible, sir?
Yeah, I'm here.
Yes. One more question from Dr. J. Jayapriya. Kindly suggest some types of HTL material, sir. HTL material. It is
like for perovskite, there are various material, I guess. Like I guess the question related to perovskite, like PCBM, PEDOT-PSS, and there are organic polymers like for the HTML. But the point is in perovskite, the stability issue. So in terms of the stability, inorganic whole transport layer becoming more attractive to increase the stability of the perovskite solar cell. That's why we want to try cadmium sulfide and cadmium oxide whole transport layer for perovskite solar cell. So the inorganic type seems like more attractive one.
Can you able to see the last one, sir? How can we improve the quality of back contact? Quality of back contact.
Quality of back contact. Let me share the. Yeah, let me share the PDF. So the back contact means I will share the point from here. So looking at this structure, this configuration, the substrate and superstrate. So in figure A, there is a moly-based contact, and in this one we have only just silver contact on the top of them. Just we use the transparent conductive oxide layer. So on the top of the moly-based substrate, the tin sulfide needs to be developed on the top of it. So during sulfurization, it might be a problem to form moly disulfide, because we use like the people use the moly-based substrate on the bottom. Once deposit the tin sulfide and sulfurize this substrate, we want like only tin sulfide, but at the same time the sulfurization go through the moly substrate as well. So moly sulfide might be a problem, especially for the recombination loss between these two contacts. So generally people prefer to use this superstrate structure, and there is no contact is not a big issue for the superstrate. So as we remember in this one, so this is our solar cell structure, and there is the real one in the solar simulator as well. So we have only just TCO on the bottom and silver or gold on the top. That's it. But in this one, the moly sulfide is a major problem. So preferring the superstrate structure provides an opportunity to have higher efficiency compared to substrate.
Yes. Any other interested participants? If you are interested in asking questions, you can unmute now. You can go for your questions. Any other interested? The option was already given. You can unmute yourself to ask your question.
Myself, Dr. M. Sumitra from VNR VJIT. Thank you, Farooq sir. It's a very wonderful and enlightening session for us. Thank you, sir.
Yeah, my pleasure, my pleasure.
Have any question, ma'am?
No, sir. It was.
Thank you, ma'am. Thank you. Any other interested? We have one more question in the chat box, sir. Under solar stimulator, how do the practical size variation affects? 1 minute. Can you able to see that, sir? Under solar stimulator, how do the particle size variation affects the output or fill factor?
Variation, I didn't get it. What does it? Particle size variation? Like during the measurement or during the process?
Jaypriya ma'am, if you can unmute yourself, you can ask your question directly.
Yeah, I guess.
So,
the solar cell measurement is critical, as I mentioned. So first of all, to optimize the sunlight, so this is the light measurement, to optimize the sunlight, 1.5 air mass, and with some international requirement. First, the solar simulator needs to be optimized through the silicon reference solar cell, which was certified by NREL. And so this measurement can be done in the air because we are measuring inorganic type. It's not that sensitive to oxygen. I guess the question is related to oxygen in the air during the measurement. So for the OPV, perovskite, or dye synthesize, these are the air sensitive products, the air sensitive solar cell. This solar simulator is in the glow box under nitrogen atmosphere. So there was no particle issue if we measured our solar cell in the glow box in the nitrogen atmosphere. So there is no like oxygen problem during the measurement. But for inorganic type, it's not a big problem. So we can basically use the setup in the air.
Stephen sir, are you interested? Stephen sir, any other interested? This is your time, you can go for it. Malia ma'am, otherwise we can go for vote of thanks.
Sir, for me, one question, sir.
Any more questions? Yeah, Manjula ma'am.
Sir, thank you, sir. Sir, actually, I'm a theoretician. We are calculating absorption coefficient along with the extinction coefficient also, because the laws that related to absorption coefficient also. So can you explain how it is extinction coefficient related to here? We are calculating extinction coefficient with the energy. I heard about an experiment in the sense wavelength with the extinction coefficient. So what is that? I mean, what does it depends on? Extinction coefficient, it depends on what are the factors. Can you say something?
Okay. Let me share again. I guess so. You asked related to band gap
Yes,
calculation. So you calculating the absorption coefficient for any kind of specific material, Dr. Manjula?
Yes, sir. We are calculating SN, SC, SNT, similarly Ca calcium telluride like that. We are calculating for absorption coefficient, all other properties theoretically. DFT study.
Okay, so so we measure the transmission to get to calculate the band gap. So in this specific region, first of all, we see the very sharp absorption threshold. So this gives an idea. So this is the good candidate for solar cell application for each material. This sharp absorption threshold. And according to Lombard's law, so there is a like incident and transmitted light based on the exponential term. Maybe you are familiar of it. Absorption coefficient and the thickness of the film. So the alpha basically absorption coefficient, thickness of the film. So this one is 100 nanometer, and ln transmission. So based on this formula, we are moving to tau relation. We are getting absorption coefficient and moving to tau relation and calculating the EG band gap from the tau relation. That's all we done.
Okay.
I can share like detailed mathematical the equation if you want, like separate Dr. Manjula.
Yes, sir. Yes, sir. Thank you, sir. Thank you so much.
Yeah, sure.
If no other questions, we can go for
One more question from Ernest Stephen.
Yes.
What is the maximum output efficiency achieved in this solar cell? He is asking that. Sir is asking.
For this one, 5. So this chart shows the highest number of efficiency for all type of solar cell, NREL PV chart. Suppose I said like cadmium telluride was the first commercial one after silicon solar cell. So 22 is the cadmium for the cadmium telluride is the highest one. For CIGS is the same one, CZTS. But this chart is emerging photoabsorber. So the record efficiency for this one less than 5%, and it's almost around the same for all emerging photoabsorber material, around like 5%. So coming back to this chart again, 4.36 is the highest one, highest efficiency for tin sulfide base, which was succeeded by MIT. Another question?
Okay, I think we will wind up the session, sir.
Yes.
Dr. Farooq, sir, yeah. Thank you for spending your most valuable time, I can tell you, with us and sharing your research activities so explicitly and explaining about DFT calculations, some characterization techniques for various semiconducting materials that are used for solar cells and solar cell fabrication process. Okay, your slide carried so much information regarding photovoltaic performance and some details on perovskite solar cells, etc. And most importantly, answering our participants' queries so patiently. I should really thank you, sir, and we hope we get another opportunity to interact with you very soon. Thank you, sir.
Hopefully.
And
There will
thanks
be a
from
chance
Manjula
to
madam.
meet
And,
in person as well. Hopefully.
yeah, sure. Yes. Yes.
All right.
Sure, sir. We will once. Thank you from our team, sir. Dr. S. Murugesan, sir, Dr.
Thank
M.
you.
Manjula, and myself, sir. Thanks a lot for being
Thank you,
here.
sir.
Thank you, Dr. Balakhan. Thank you, sir. Thank you so much, sir.
All right. Thanks. All right.
And
We have
thank you all the participants. Kindly fill your feedback forms, submit it, and I think hopefully we will meet tomorrow in another interesting session. And if there's time, Dr. Farooq also kindly join with us in case you have time to spend with us. Thank you,
I can stay. Of course.
You're welcome, sir.
Dear participants, 2 more minutes will be given to fill up your feedback form if it is not filled up. Once already filled up, okay, no need to go for it again. 2 more minutes will be given. Link is provided in the chat box. Once again, I'll try to give you now. Link, feedback link is provided. You please go for the feedback form. Carefully fill it up because this information provided by you only, this will be reflected in your certificate. If you do any mistake, that will also be reflected in your certificate. That's what, take your own time to fill up this form. Angela ma'am, is it enough?
Yes, sir. Yes, sir. We'll wind it.
Dear participants, time almost over. We are going. This is the time for winding up the session. We'll meet you tomorrow. Thank you all. Thank you all the participants.
Thank you, participants. Thank you, sir. Thank you so much.